Hello, my name is Jim Haney, and today we're going to be reviewing how to use OpenRocket to design high-powered rockets. OpenRocket is a free and open source software that gives us the power to design and simulate what a rocket will perform like before we actually build it. To learn more about OpenRocket and to download it, click the link in the description. Let's walk through all the steps required to build a basic level 1 high-powered rocket. To start, let's make the general shape of the rocket. Under the Add New Component window, let's click the nose cone. Every time you add a new component, it will ask for some general information about the component. Don't worry if you don't know all of these numbers, you can go back and change them at any time. So we're going to have a nose cone, and we're going to make it out of just some general plastic. If you're 3D printing, for example, a nose cone, it doesn't always have the material there, so we could just choose something that's close enough. And even if you don't see something exact, the material of the nose cone is only used to auto-calculate its weight. You don't need to worry too much about that. Then let's say that the nose cone itself is 8 inches long. I know this just from the supplier's website, and I know it has a base diameter of 3 inches. If you don't want to design in inches, you can click on any of the units and select a new unit from the drop-down. Also, based on the manufacturer's information, I know that this nose cone has a shoulder with a diameter of 2.9 inches and a length of 4 inches. Once we're done with that, we can click the close button. If we ever want to go back in and edit those again, we can double click on the nose cone in our rocket tree. Now let's add the body tube of the rocket. To do this, we'll click the body tube button under Add New Component. Set the length of this one to 24 inches, outside diameter of 3. If you notice this automatic button is checked, what this will do is it will take the same outer diameter of the part above it. Since the nose cone had an outer diameter of 3 at the base, it'll make this part 3 inches. And if we add any more body tubes after this, they'll all be 3 inches as well. Call the inner diameter 2.9, and we'll say this is made of cardboard. Now we need to add the fins to this rocket. If you notice, when I click on a part, a lot more options become available in the Add New Component menu. Certain components can only be placed at the top level, such as nose cones, body tubes, and transitions. But inside of different components, there are other objects you can place. For example, in a nose cone, you can place pretty much everything except for a fin. And on a body tube, you can create anything. Let's add some fins to the bottom of this rocket. I'll click trapezoidal and set it to 4 fins. We'll make them out of balsa wood at 1/8 of an inch thick. We'll also give them a 1/4 inch fillet, which is probably a bit extreme for this, but it'll work for now. Now there's an awful lot of settings here on how you quantify a fin. I'd suggest, if you're new to the software, that you just take the window and you go through and you adjust each setting one by one to see what it actually does. For instance, fin rotation will offset them around the body of the rocket. Fin cant can be used if you wanted your fins to be bent over for some reason, such as to increase the spin of the rocket during flight. The root chord refers to the length of the part of the fin that is touching the base of the rocket, and the tip chord is the same except for the top of the fin. The height is just the difference between those two. The sweep length refers to how far back swept the distance is between the two chords, and the sweep angle will define how extreme the angle is between the body and this leading edge. You'll notice that when you modify some of these values, it will automatically update others to make everything work. OpenRocket will never let you input an invalid component. Anytime you put in a new input, it will automatically change everything else. So sometimes you need to be careful when entering multiple values to make sure that everything stays how you want it to. Non-top level components also have a position relative. This is how you determine where this component will stay on the rocket. Fins we usually want towards the bottom of the rocket, so we could say, relative to the bottom of the component, move them nowhere. Now, if you had a component like, say, a bulkhead that you wanted to always be within an inch of the top of the rocket, you could say top of the parent component, tip of the nose cone, etc., and then input a value. And you can see now it'll move all the way up so that it's just 2 inches from the top of the rocket. Let's move that back down to 0. Now I'm sure you're wondering where I'm getting a lot of these values from for the body tube size and the nose cone size. Stock components like that, you're going to have to do some research and start to find different suppliers who provide those components pre-made. Things like fins, though, we have the freedom to manufacture them ourselves, so they can be whatever shape we want. Let's go back into this body tube and let's add an inner tube. The inner tube we're going to use to mount our motor. So let's go to the motor tab and click this component is a motor mount. This now allows us to modify some settings about the motor. The most important one here is ignition at. If you had a multi-staged rocket, you could set it up that this motor ignites when the motor below it has burned out. Since we're just building a single stage rocket, we could set that to either be automatic or launch. If you wanted to have, say, 3 rockets at the base of your rocket, you could arrange multiple tubes in a pattern. Looking at this side view of the rocket doesn't make it very obvious that there's 3 tubes there. So let's real quick just change our view, and now it becomes a lot more apparent. Changing these views helps to better visualize your rocket as you're designing it, so I suggest regularly switching between them. Let's change that back to 1 and select a motor. Now for this rocket, I've already decided that I want to use an H195 NBT. This is a very common level 1 certification motor. So what we can do is go to our Motors and Configurations tab, click New Configuration, and then select what motor we want. So we set an H195 NBT. If we hit OK, it'll put the motor into the rocket. The gray outline shows where the motor will be. Now obviously there's a challenge here that the inner tube is smaller than the motor, so we're going to have to adapt that. If you're set on the size of your inner tube and you want to find motors that will fit into it, another thing you could do is in the Motor Selection tab, limit the diameter and length of the motor to only things that will fit inside of that rocket. So as you see, if we limit it, we now have this list of engines that'll work. You could also sort by manufacturer or the total impulse of the engine. Let's change those back to the defaults and get our H195 in there. Now we need to change the internal diameter and length of this tube to match. If we look at the H195, we can see it has a diameter of 1.14 inches and a length of 8 inches. So let's go back to our rocket design tab, select the inner tube, and change the inside diameter to 1.41. I believe is what I said. Oh. You notice how it didn't change past 0.748? That's because OpenRocket will not let us set the inner diameter greater than the outer diameter. I'm going to 3D print this tube myself, so I don't really need to match it to any manufacturer specifications. So let's just say that it's 1.45 in diameter, and the ID is 1.41, and now hopefully that should match our engine. I'm just going to go back into the Motors Configuration tab and double check. Oh, look at that, I messed up the number. It should be 1.14 inches. 1.14. And we'll change the outer diameter to let's say 1.2. We can then set the length to be 8.5, make it slightly longer than the engine. And there we go. And the material, we can leave it as cardboard for now. That's close enough. Although actually, if we're going to 3D print it, let's change it to something like PVC. Now you notice when I change that, these two, or this ball here rather, will move relative to this ball. The blue and white ball is our center of mass. This is if we were to balance this rocket on a wire or a small beam, that is where the rocket would naturally balance. Below that, the red dot is the center of pressure, which is calculated through some advanced math related to the aerodynamics of the rocket. Essentially, though, those two positions tell us how well our rocket is going to fly. You can see up here, our stability is 0.624 cal. That's based off of the position of the CG and the position of the CP. A cal is the diameter of your rocket. So since this is a 3-inch diameter rocket, 1 cal would be 3 inches. Generally, you want your rocket to be between 1.5 and 2.5 cal for safe flight. If it's less than 1, the rocket has a risk of flipping over and coming back towards you. And if it's too high, there's a risk that the rocket will try to fly horizontally. So to change that value, we can either move the CP backwards or move the CG forwards. We're not quite finished designing the rocket yet, so let's not worry about that too much. But as we're positioning components, it's definitely something to think about. Let's say on the inside of this rocket, I want to include a small GPS tracker in the nose cone. We want the nose cone to be sealed so that the charges and forces from the engine don't blow up into the avionics bay. So I'm going to put a bulkhead at the bottom of the nose cone. I'm going to make it 0.125 inches thick. And you can see it's positioned there relative to the bottom of the parent component, which in this case is the nose cone. But I really want it to be down here at the bottom of the shoulder. So what we can do is move that backwards, 3, 1, just to right there. And we're going to set the material for that to basswood. Now obviously you don't really want to go through and design your entire avionics board in here, so we're going to use something called a mass component. The mass component allows us to tell OpenRocket the weight of something that's too complex to model. So I know that my avionics board and its battery and its transmitter all together is going to weigh about 200 grams. If I wanted to check things for sizing and positioning, I could also adjust the length and diameter. But for now, I'm just going to position it about where the center of mass of those components will be. You can see, since this is such a heavy component, the center of gravity is moving along with it. I'll put it about there. Now if I wanted this to look a little bit nicer as well, what I can do is go into my mass component and change the mass type to, say, a flight computer or an altimeter. This will then give me a better indicator icon on the mass component to help me differentiate between batteries, altimeters, weight that's added to improve stability, etc. Now that that's in there, let's take a look at recovery systems. Again, before we started, I went onto a manufacturer's website and I found a 36-inch parachute that I want to use for this. So let's go into the body tube and place our parachute. I know the parachute is 36-inch diameter with a 0.8 CD. Those are both values just taken directly from the manufacturer. And I know that the parachute weighs about 2.5 ounces. The challenge is, right now OpenRocket is calculating that it's going to weigh 1.67 ounces based on the density of the material used. If I don't agree with what OpenRocket is saying, I can go into the Override tab, click Mass, and then input a new value. I could also override the center of gravity if an object's center of gravity is not exactly in the center of the object. Although more often than not, it's easier just to keep that at 0. Now we can position the parachute by moving it backwards using the position relative to top of parent component plus 7 inches. The parachute will just be free floating in this area underneath the nose cone. I also know that its packed length overall is 5 inches by about 3 inches. And let's move it back that way a little, just like that. I then also know that underneath that I have the shock cord. There's no specific shock cord item in the mass component, so I'll just use recovery hardware, and I know that I have 1 ounce of that. I can then move that down using this button to right about there. Now the last thing we need to do is adjust the mechanical components of the rocket. Right now this tube is not actually connected to the rest of the body of the rocket. We're going to have to add some spacers and a bulkhead to the top of it. So let's start by adding a centering ring. We'll make all of our centering rings out of basswood with an outer diameter of 2.9. That's automatic to match the inner diameter of the body tube, and an inner diameter of 1.2, which is automatic to match the outer diameter of our motor tube. We'll set this thickness to 0.125, and then we will put one down at the bottom. In fact, the one at the bottom, we're going to make twice as thick, sandwich 2 of them together, since that's where a lot of the force of the engine is going to be coming through. Then we can select the centering ring in our rocket tree, hit Control-C, and then Control-V to make another one. This one will adjust to 1.25, and we will move it up. This will help to better locate the engine tube inside of the main body tube. Now that's all set, we have our rocket roughly how it's going to look on the pad. We see that our stability, it actually worked out pretty luckily. It's pretty stable right now. However, let's say that it wasn't quite stable or something was off. Maybe our fins happened to be a bad shape. And they were like that. Well, now all of a sudden we're not stable at all. We need to begin moving things to make everything more stable. We can either move the center of pressure backwards by moving things like the fins back, or the center of gravity up by moving heavier objects up this way. The most common way to balance a rocket is to add more mass to the tip of the nose cone. Usually lead or steel shot is used. In our case, though, we can make these fins a bit more reasonable. Let's change the root cord to be a lot smaller. And let's make them about like that. Having wings that sweep past the back of the rocket is a little bit dangerous during descent. There is a chance that the fin will hit first, and there's a lot of twisting momentum on it as the rest of the rocket comes down. However, I'm confident in how well we're able to glue these in, so I think it'll be okay. Now, if we wanted to manufacture these fins, we're probably going to laser cut them. And to make laser cutting a lot easier, OpenRocket allows us to actually export this shape to the laser cutting software directly. But we want to make sure that we have the entire shape of the fin there when we go to do that. The one thing that we're missing is the fin tab. This is how the fin is actually attached into the rest of the rocket. What we can do is, in the tab section, we can define a fin tab by its height and its length. Something like that should be good. Now we pretty much have a flyable rocket. Let's see how well it's actually going to perform. We have our entire rocket design set. We have our motor set. Now let's go to the flight simulation tab. By default, one simulation will be generated for each motor that you install. So if I wanted to compare an H195 to another motor, I can create a second configuration, choose another motor. Oop, that's a bit of a big motor. Let's limit it to only things that'll fit. There we go. That's a way underkill motor, but it's a good comparison. We now have a simulation for each of those. You can select a simulation and click the Run Simulation button, and it will then run through what's going to happen. Let's do that for both of them and compare what we get. So with the H195, we have velocity off rod of 122, which is beyond acceptable. We have an apogee of just under 3,000 feet, velocity at deployment of only 15 feet, which is good. Optimum delay of 10 seconds, which is good since this is a 10-second motor. Max velocity is reasonable, max acceleration is reasonable, time to apogee is reasonable, flight time is reasonable, and the ground hit velocity is safe. Overall, that's a good motor. Simulation 2, obviously not that good. Velocity off rod is pretty slow. It's only going to go up about 150 feet as well. Now, one thing to note is that when we change that motor, OpenRocket automatically accounts for the change in weight. You could see down here that the CG and the CP have changed since we have a much smaller motor. You can switch back between the two by choosing a new motor from the flight configuration menu. This allows you to check the flight performance with multiple different motors, even if they're not the same size. For more information on how to interpret simulation results, check out one of our upcoming videos on how to understand flight performance. Let's say that we wanted to try some other simulations. Maybe we were going to launch this rocket in upstate New York, but then I'm also going to go and visit my family in California and launch it out there. Let's make a new simulation using the H195 motor, and I can look up the information related to the new launch site that we're going to be traveling to. I can get information about what the average wind speed is, the turbulence, the altitude, all things that will have an impact on the rocket. Let's say that I know that at this new launch site there's almost no wind. It's about 1 mile per hour average. But it's way up in the Rocky Mountains. We're talking over 7,000 feet above sea level. If I simulate that, we could see at the new higher altitude, the rocket actually gained almost 400 feet on the apogee. That's because the atmosphere will be thinner the higher up we are. If I wanted more in-depth information about either of these simulations, I can click on one and hit the Plot Export button. I can then export the data as a CSV, and I can determine what will actually be exported, or I can plot it. Let's say that I want to plot the time versus the altitude. Once I select that, I can hit the plot button, and it'll tell me everything I need to know. It will also give us information about specific events during the flight, such as when the recovery objects deploy and when the motor ignites and burns out. This is also useful for determining how far your rocket's going to drift. We can set the x-axis as altitude and the y-axis as horizontal distance. Where is that? Lateral distance. If we plot that, this will show us that the rocket will take off at the launch pad. It will continue to fly and it'll move, and then once the parachutes deploy, it'll start drifting backwards based on the wind conditions, and it'll end up almost a half mile away from the launch site. Definitely not something too good. We might want to consider putting in a smaller parachute or changing around the deployment system. If you're designing a very complex rocket and you need to hit a certain altitude goal, you can use the Rocket Optimizer to change around parts automatically. Let's switch back to the H195 motor and say that we want to change around the fins. We can go to Tools, Rocket Optimization. Inside of the Rocket Optimization, we can select certain characteristics of each component and change how they are. OpenRocket will then automatically vary these characteristics and simulate the rocket to determine what is the best value. Let's start by going to the trapezoidal fin set, and let's say we want to change the height, the root chord, and the tip chord. We could then give it a min and max value, and say that using the H195 motor, we want to maximize our apogee, get as high up as we can, but we need to keep at least a 1.5 stability. Once that's all in, we can hit the Start Optimization button, and OpenRocket will start running through new fin designs for us. Now you can see with this new fin set, it has gotten us to 3,050 feet, versus the previous expected, which was 2,992. Not very much of an improvement. You could also see that OpenRocket doesn't really think about how safe or effective a design will be. These fins are very thin and long. They're probably going to snap if we try to fly this rocket. If we're not happy with what it did, we can hit the reset button. Let's try modifying something else. Let's say that we want the rocket to come down as close to the landing site as possible, but we don't want it to fall too fast. What we can do is optimize for landing distance, and we want to minimize that. We want to land as close to the launch site as possible because we're all lazy and we don't want to go for a long walk. We can then give it our parachute diameter, tell that it's currently 36. The smallest parachute I'm willing to fly is a 12-inch, and the maximum is a 72. I can then tell it to start that optimization, and it will find that I can get it down to 535 feet away from the launch site if I use a 12-inch parachute. Now again, OpenRocket's not considering all the other concepts with this. It might be that a 12-inch parachute has me hitting the ground too fast for it to be safe. I'd recommend definitely messing around with the rocket optimization and doing different things to see how it impacts your rocket. Let's say that you design your rocket, and once you've built it and put it all together, you go to measure the CG, and it turns out that it's not actually where you expected it to be. Let's say that maybe instead of being at 17.4 inches, it's closer to about 20 inches from the nose cone. What we can do is select the entire rocket, which is labeled sustainer here, and override its center of gravity to 20 inches. Obviously, this rocket's not going to fly very well now. Let's say that we measured it and it was actually closer to 12 inches. We can then override it using the override center of gravity option, and it will move it back to adjust. You can also use this to override the mass of your rocket once you assemble it. Keep in mind that the sustainer mass does also include the mass of the motor. If you want to modify it without the motor there, you can change to no motors. If you were modifying the mass of something like the body tube or the nose cone, you can hit the override mass and CG of all subcomponents. When you're just overriding this mass here, all it's changing is the mass of the physical nose cone itself. When you click this button, it's now assuming that you're measuring the mass of the nose cone with its bulkhead and all the avionics inside of it. This can be really good at fine-tuning a simulation to ensure the best performance of your rocket. That's all there is to designing a basic rocket in OpenRocket. I look forward to seeing what new and exciting rockets you come up with.